Greetings to all and welcome to this lecture. We are in module 11 small signal modeling, lecture number 5, a low frequency small signal model part 2. In this lecture we are going to see how we can derive those small signal parameters what we have defined in previous lecture under strong inversion region of operation. So, we will see how we can derive the gate conductance, substrate transconductance, source drain conductance, output conductance, and we will also see what is the impact of extrinsic resistances on these parameters. These are the learning outcomes of this lecture, which helps you to understand how the parameters of small signal model like GSD, GM, GMB can be derived in different region of operation and how these parameters are interrelated to each other, how we can define the properties of a particular MOSFET by using these parameters. So, let us do a quick recap. In previous lecture we said that input signal magnitude is very small and also the frequency is small, then we can do a low frequency small signal modeling of a MOS transistor. We said that when the input voltage is varying very small, then the output variation in the current is also very small, and hence we can linearize the system. We can simply say the change in the current with respect to the change in the voltage can be represented by a circuit element which is nothing but a conductance. This is only possible when we are linearizing the system considering small signal model. Further, we also said that in small signal model our superposition principle holds good, meaning we can find out the total perturbation in the drain current by considering the perturbation of gate to source voltage, gate to body voltage, or gate to source voltage, body to source voltage, and drain to source voltage separately, right, such that the overall perturbation in the current can be given as the superposition of these perturbations. We also said that if we relax the assumption of considering Ig is equals to 0 and Ib is equals to 0, then the overall small signal model can be given by this, which says that between each terminals we do have some circuit element, whether it is conductance or transconductance. Similarly, we said that there are some voltage dependent current source which reflects the change in the output current with respect to change in the terminal voltages. We also said that we can define this definition with some alternative way, like considering the individual terminal voltages with respect to a particular reference or a common reference as a ground. So, instead of defining the voltages between two terminals, like instead of defining VGS, we can simply define as Vs, which is a voltage of source with reference to some common reference as ground. Similarly, this gate can be defined as Vg. Similarly, the drain can be defined as Vd, and so on. In addition to that, we can calculate the change in IDS with respect to change in Vg, right. So, we define alternatively the definition of these conductance or transconductance parameters. Now, let us see how can we calculate these parameters under different regions of operation. In the first go, we considered the strong inversion region of operation. We know that the current equation in strong inversion region of operation can be given by W divided by L mu into COX dash VGS minus VT into VDS minus alpha into VDS square divided by 2. We define this current equation under non saturation region. So, IDSN, whereas in saturation region we defined as IDS dash is equals to W divided by L mu into COX dash into VGS minus VT whole square divided by 2 into alpha. Now, let us calculate GM, which is defined as the change in the current with respect to change in VGS. So, we can define the transconductance, right, for two different region of operation, one is non-saturation and one is saturation. So, if we differentiate it, let us consider it for saturation region of operation. So, VGM is can be defined as W divided by L mu into COX dash divided by 2 into alpha VGS minus VT into 2, where this 2 and 2 get cancelled. VGS minus VT divided by alpha is can be defined as VDS dash. So, this GM is defined in the range of saturation condition, whereas in non-saturation condition you can define GM as W divided by L into mu into COX dash into VGS minus VT into VDS minus alpha into VDS square divided by 2, and you need to differentiate this with respect to VGS, right. So, from here you will get GM is nothing but W by L mu into COX dash into VDS. We get to clear picture of GM in saturation and in non-saturation region. In non-saturation region, the GM is not dependent on VGS, right, it is a function of VDS. So, GM in non-saturation region is function of VDS, whereas if you see GM in saturation, then it becomes a function of VGS. We can simply identify this by this equation. We can simply identify this by the output characteristic, which is plotted here. The output characteristic plotted between drain current and drain voltage. You see here this region of operation is non-saturation, where VDS is very very small. So, this is non-saturation. In non-saturation and this region of operation is saturation region of operation, right, when VDS is increases beyond a particular VGS minus VT. Then if you closely observe, these are the lines for different VGS, right. So, let us consider this is VGS 1, VGS 2, VGS 3 and VGS 4. So, the gap here is the change in the current per change in the voltage, which is nothing but GM, and as you are changing VG, the GM is not changing. So, the difference here is almost constant, right. That is what the meaning, the GM in non-saturation region is only dependent on VDS and not VGS. So, it is not dependent on VGS, whereas if I take a cut line at B side, again the difference is same, it means the GM is not function of VGS, whereas when you change the cut line from A to B, it is changed, right, the GM is changed. So, GM is a function of VDS and not VGS, whereas if you see this scenario in the saturation region, in the saturation region this is one point and this is another point. So, the GM is not changing with respect to VD, right, whereas if you change VG, the GM is changes, right, but with respect to VD it is not changes. So, GM depends on VGS in saturation region, right. By solving this equation, we can propose different models or different way of representation of GM. For example, the one way of representation of GM, what we calculated as W divided by L mu into COX dash divided by alpha into VGS minus VT, right, which is this equation. Now, can I replace this VGS minus VT by this current equation? So, VGS minus VT can be written as 2 into alpha divided by 2 into alpha into IDS divided by W by L into mu into COX dash. Now, if you put back here, you will ultimately left with 2 IDS divided by VGS minus VT, which is this equation. Similarly, in one way you replace this parameter from the current equation and ultimately you will ended up with this equation. So, we can simply say in a strong inversion region of operation, we can define GM in 3 possible ways, right, which is given by this. Now, let me ask a question. What is GM at VGS is equals to VT? So, find GM at VGS is equals to VT. Now, if you see this equation will give you GM is equals to 0, because when you put VGS is equals to VT, the first equation will give you GM is equals to 0, whereas the third equation will give you GM is equals to infinity, because VGS minus VT is coming in denominator. So, how it is possible? Strictly speaking, we derived this GM model for strong inversion region of operation, whereas when you are considering the case VGS is equals to VT, this is not in strong inversion, this is in weak inversion nearby, right. That is what we can say, the calculation of these parameters are strongly dependent upon the region of operation, the parameter of the values, where the voltage is applied, in which, between which terminal the voltage is applied, and so on, right. That is what you cannot simply use the models which is derived for strong inversion in weak inversion. So, you have to have a separate region of modeling where GM can be given by different equations in different region of operation. So, actually if you see what GM is nothing but the change in the current with respect to change in voltage. So, we can understand this GM as a slope of transfer characteristic, which is nothing but given as this, and this value is approximately threshold voltage, right. So, the slope is nothing but what? Transconductance. GM is nothing but the slope of delta IDS divided by delta VGS characteristic. So, for sake of simplicity, let us consider that GM for two different positions of this slope. In the sense, let us consider two GM values, one I am measuring here and one I am measuring here, right. Let us consider this GM is GM2 and this GM is GM1. Which is higher GM? GM2 is higher because the slope is higher following a square law dependency. This GM2 can be defined as the slope or this particular, for a particular current, delta IDS divided by delta VGS, right, delta. So, GM2 is higher, but the current corresponding to GM2 is also higher, the IDS2 is higher. Similarly, GM1 is lower, but the current corresponding to the GM1 is also lower, and hence if you want more GM, you need to pay the cost for more current and hence more power dissipation. That is what, there is always a trade off between GM and ID or the power. We can define a figure of merit as GM by ID as a transistor efficiency, right. So, this is what you want, this is desired, you want higher GM, right, but this is what you are actually paying the cost, because the current is also more. So, you should have a trade off, proper trade off, what you are actually looking for. Now, this GM calculation depends on several factors, as we have seen that when we are considering this current equation, then we have ignored the channel length modulation, but when you are talking about the short channel devices, then several factors comes into picture like CLM, channel length modulation, Dibble, velocity saturation, and so on, which simply says that the current is no longer completely square dependent, right, and we do have several factors, and while calculating GM we need to consider these factors to get the precise calculation of transconductance. Let us take an example. If I consider a short channel device where the velocity is saturated such that the current can be given by W into Q into Vd max, right. Here Q can be written as W into minus of Cox dash into Vgs minus Vt, right, into Vd max. Now, when you are going to calculate GM, so GM is nothing but delta IDS divided by delta VGS, which is nothing but W into COX dash into VD max. So, GM is now changed. GM is no longer dependent on VGS minus VT. Because of velocity saturation, it depends upon the saturation velocity of the carrier. This can be simply rewrite as COX dash into mu into EC, where EC is a critical electric field. That is what we have already discussed when we were discussing about the velocity saturation. Now, let us calculate the another parameter, which is substrate transconductance in strong inversion. We know that the substrate transconductance GMB can be given by delta IDS divided by delta VBS, meaning the change in the output current when the body to source voltage is changing. In strong inversion region of operation, the current can be given by this equation, and we also know that VDB and VSB can be represented in terms of VDS and VGS. So, this representation is for body reference and this representation is for source reference. So, we can rewrite this equation as IDSN is equals to W divided by L mu into COX dash into VGB can be replaced as VGS plus VSB minus V flat band voltage into VDB minus VSB can be written as VDS minus half of phi naught plus VDS plus VSB square minus phi naught plus VSB square minus 2 by 3 gamma times phi naught plus VDS plus VSB to the power 3 by 2 minus phi naught plus VSB to the power 3 by 2. So, I change the reference from the body reference model to the source reference model. Now, I can simply calculate GMB as GMB is equals to delta IDSN, where N stands for non saturation region with respect to VBS. Make sure here this is VBS, body to source voltage. We have discussed in previous lecture that we are applying the body to source perturbation, whereas here this is VSB, right, to maintain the reverse bias at source to body junction. So, mu into COX dash into, if I differentiate this, you will get VDS common, and the differentiation of VSB with respect to VBS will give you what? Minus 1. Is that okay? Because VSB is equals to minus of VBS and you are differentiating with respect to VBS. So, you will get minus 1 minus half, this will give you 2 times of phi naught plus VDS plus VSB. Again the differentiation of VSB with respect to VBS will give you what? Minus 1 minus 2 times of phi naught plus VSB into minus 1 minus 2 by 3 gamma, and this will give you 3 by 2. The same thing will be repeated here, phi naught plus VDS plus VSB with a minus 1 minus phi naught plus VSB into minus 1. So, this can be written as W by L mu into COX dash minus of VDS. Now, you take 2 common. So, this 2 and 2 will get cancelled and take minus common. So, plus phi naught plus VDS plus VSB, and as you have already taken this minus out and 2 out, you left with minus phi naught minus VSB minus this 2, 2, 3 and 3 get cancelled, you left with minus gamma, right. Then sorry, this is the power of 1 by 2, right. Take minus common, so it will become plus, you will left with square root of phi naught plus VDS plus VSB minus square root of phi naught plus VSB, correct. Now, this get cancelled, this get cancelled, this and this get cancelled. So, you are left with this W by L into mu into COX dash gamma square root of phi naught plus VDS plus VSB minus square root of phi naught plus VSB. This is GMB. We can again solve this by factorizing as GMB is equals to W by L into mu. So, I am solving it here into COX dash into gamma divided by phi naught plus VSB plus VDS plus square root of phi naught plus VSB, and in numerator you will get a minus b into a plus b as a square minus b square. So, phi naught plus VDS plus VSB minus phi naught minus VSB. So, this and this get cancelled. You will left with W by L into mu into COX dash into VDS into gamma divided by square root of phi naught plus VSB plus square root of phi naught plus VSB plus VDS, right. In the previous expression you can simply find out that W by L mu into COX dash into VDS is what? GM here, right. So, I can simply use GM here as GMB is equals to GM into gamma. Now, here I will use an approximation as if I do have a factor like 1 over square root of A plus square root of A plus B, then for simplification I can rewrite as 2 times of square root of A plus some constant into B. This is same as at B equals to 0. So, at B equals to 0 if you calculate, this is same. So, when B is very small you can use this approximation, right. That is what we are going to use as this is A. So, I am going to use as square root of 2 into A, which is phi naught plus VSB, and what is B is VDS. So, I need to represent as K times of VDS. So, this is an overall expression which is GMB is equals to, so I can show it here, GMB is equals to GM times gamma divided by 2 into square root of phi naught plus VSB plus some K into VDS, right. Now, we know that a factor eta, which we have defined in our previous lectures as 1 minus VDS divided by VDS dash. So, VDS can be written as VDS dash into 1 minus eta. So, I replace this here and I will ultimately ended up with this equation. So, this factor gamma divided by 2 times of square root of phi naught plus VSB plus some constant K into 1 minus eta into VDS dash is defined as BG, right. Now, I can simply say the transconductance, the substrate to body transconductance or the substrate transconductance is nothing but GM into BG, right, which is here. Now, let us do a further simplification. As I said that this holds good when the voltage is very small. If the voltage VGS or VDS is very small, I can simply ignore this factor and BG can be written as gamma divided by 2 times of phi naught plus VSB. If you recall, this is nothing but alpha 1 minus 1. In the source reference model we defined alpha, where we said that alpha 1 is nothing but 1 plus gamma divided by 2 times of square root of phi naught plus VSB. So, this factor is nothing but what? Alpha 1 minus 1, or we have also defined this is nothing but n, right. N is the slope factor. So, I can simply rewrite this equation as Bg is equals to GMB divided by GM is equals to gamma divided by this is equals to alpha minus 1 is equals to n minus 1, where n is defined as 1 plus C B dash divided by C O x dash, right, the bulk capacitance over the oxide capacitance. Here we are considering that there is no interface trap charge. Furthermore, we can define this factor gamma divided by 2 into square root of phi naught plus V S B in terms of threshold voltage. Remember, V T is equals to V T naught plus gamma times square root of phi naught plus V S B minus square root of phi naught. These all equations we have defined in our previous lectures. So, if you take a differentiation of threshold voltage with respect to V S B, you will ended up gamma divided by 2 times of square root of phi naught plus V S B, because this is constant, right. So, you can replace this factor by V T divided by delta V T dVSB also, considering the VGS and VDS is small. So, here what we are doing, we are interrelating the small signal parameters. This factor GMB by GM actually reflects the control of gate voltage or the control of gate and the body in the channel, which means, as I said, that this can be defined as GMB divided by GM can be defined as n minus 1, where n is equals to 1 plus CB divided by COX dash. So, GMB divided by GM can be defined as CB dash divided by COX dash. CB dash is nothing but what? Epsilon of semiconductor divided by dm or dBm into epsilon of aux into Tox, where this is the depletion region thickness. Now, this shows what is the control of gate or the body in the channel. If, let us consider, the oxide thickness is very small. If the oxide thickness is very small, it means this factor is very small, which means the gate control is more in the channel as compared to the body side. If dm is large, meaning the depletion region in the channel is large, that means this is small and hence the gate control is more over the body. That is what the basic physics what we have already discussed, how the gate and the body controls the channel. So, this parameter actually relates the controllability of the gate and the body. Now, let us define the another parameter, which is source drain transconductance, right, under strong inversion. So, the source drain transconductance is can be defined as GSD is equals to delta del IDS divided by delta VDS. We have just seen the current equation in strong inversion can be written as W divided by L mu into COX dash into VGB minus V flat band voltage into VDB minus VSB minus 1 by 2 VDB plus phi naught whole square minus VSB plus phi naught whole square minus 2 by 3 gamma VDB plus phi naught to the power 3 by 2 minus VSB plus phi naught to the power 3 by 2. Here again VDB is what? VDS plus VSB, right. Similarly, VGB is what? VGS plus VSB. Now, you replace VGB by VGS plus VSB, VDB by VDS plus VSB and differentiate now with respect to VDS. So, the first term you will get W by L mu into COX dash into, here you will get what? VGB minus V flat band voltage, we are replacing as VGS plus VSB minus V flat band voltage, and this is VDS. So, we are differentiating with respect to VDS will get the same parameter minus half, this will give you 2 times of VDS plus VSB plus phi naught, right, and this is 0 minus 2 by 3 gamma into 3 by 2, again this will be VDS plus phi naught plus VSB. This gone and this 2 and 2 get cancelled. Ultimately, if you rewrite this equation, you will ended up GSD is equals to W by L into mu into COX dash into VGS minus, you will get VDS from here, VDS minus this VSB and this VSB will get cancelled. So, you will get minus V flat band voltage minus phi naught minus gamma times this is 1 by 2 square root of VDS plus phi naught plus VSB. So, this is a closed form equation which is given here. We have another approach to calculate the source drain transconductance. How? Because we know the simplified model of current in the non saturation region is can be given by W by L mu into COX dash into VGS minus VT into VDS minus alpha into VDS square divided by 2. So, we can simply calculate the source drain transconductance or the source drain conductance as W by L into mu into COX dash, differentiate with respect to VDS, you will get what? VGS minus VT minus alpha into VDS, which is given by this. So, we do have two equations for the current, one is a lengthy expression and one is the simplified version. We have seen that when we plot the current equation, then this is approximately same, right. For example, this line 1 is the equation what we have written here, right, the complete detailed equation, and the solid one is the equation which is given by this. Now, if you find out the error between these two graphs, it is very less, it is almost 1% or 2% error, meaning the modification or the simplification what we have discussed in our previous module while calculating the current is so far so good. However, in the previous modules also we discussed that when you find out the differentiation, right, of these current, then the error will become large. That is what it shows. The error between these two equations of the same GSD will give you a huge difference. So, the error approximately here is 50%, meaning when you are actually calculating the source drain transconductance or the derivative of the current with respect to particular voltage, then you need to take care all the precise modeling picture. So, we can say we omitted some parameters or some inclusions like CLM, Dibble, etc. So, if you include those, then might be the error will get reduced. So, one way out is, let us consider in the current equation we do have CLM, right. So, we know that in the saturation region we have CLM and CLM is channel length modulation. So, the current is can be given by I dash into 1 plus LP divided by L. You can refer the lecture related to the channel length modulation where we have defined all these parameters, what is LP, what is LA, etc. Now, if I am interested in GSD, which is nothing but delta IDS divided by delta VDS, then I can simply take this as constant and this will become delta LP divided by delta VDS into 1 over L, right. And here LP is defined by this equation, considering the pseudo 2D model what we have discussed already in the module or in the lecture when we discussed about channel length modulation. So, LP is given by this. So, DLP divided by DVDS is can be calculated as LA, as this is a log function, you will get VE plus VDS minus VDS dash divided by VE into 1 over VE. So, this and this get cancelled, you will left with GSD as IDS dash divided by L into LA divided by VE plus VDS minus VDS dash. This factor is defined as VAW. So, IDS dash divided by VAW, where VAW is function of VDS, which is early voltage, meaning when we were defining the early voltage, what we said is you take the output characteristic, extrapolate, and this value is what? Early voltage, right, between IDS and VDS. This is early voltage. There we said that early voltage is constant. However, the early voltage is not constant, it is a strong function of VDS, which gives you the actual picture or the precision in calculation of GSD, right. That is what we have to include the short channel parameters like CLM, Dibble, velocity saturation, etc., to reduce this error, to find the precise GSD value. Let us do another attempt to include Dibble. We said that when the drain induced barrier lowering comes into picture, meaning this is source channel barrier, right, and this is the drain voltage. So, the drain voltage affects the threshold voltage, and hence my threshold voltage becomes the function of VDS. In that condition also my GSD changes, because I can rewrite the equation as W by L mu into Cox dash into 2 alpha into VGS minus VT. Now, the VT becomes function of VDS, it is no longer constant, and now when you are going to calculate GSD, then what will happen? W by L into mu into Cox dash divided by 2 alpha, this will give you 2 times of VGS minus VT, where I considered VT as constant now, but you have to calculate delta VT divided by delta VDS, and because of negative sign, because of this negative sign, here negative will come, right. So, in GSD this factor should be multiplied, that will actually reduce your error. Now, what is VT under Dibble condition? We have seen that the overall threshold voltage is can be given by change in threshold voltage plus delta V Dibble. So, please refer the lecture related to drain induced barrier lowering, where you will get what is the equation for delta Dibble, which is given by this equation. Now, when you calculate the change in the threshold voltage with respect to change in drain to source voltage, you will get, because of this minus you will get minus, because of this you will get e to the power of minus L by lambda, because here the VDS function is coming up, right. You put back this delta VT by delta VDS, this minus and minus get plus. So, ultimately overall GSD can be given by this equation, right, where you can simply rewrite that equation as GSD divided by GM, which is nothing but exponential of minus L by lambda, where lambda is can be defined as here epsilon S into Tox into dB divided by epsilon x into B3 or beta 3, which is constant or fitting parameter. So, here from here we can define GSD divided by GM. Again you see, this is the correlation between two small signal parameters. Let us consider in the previous analysis, as in the previous analysis we said that body act as a second gate. Now, let us consider this drain act as a second gate, meaning if you increase the drain voltage, considering the channel length is very small, then what happens is the control over the gate or over the channel is influenced by the drain, right. That is what we define GSD per GM is now controlled by the drain side, right. That is what we can say, the drain is act as a secondary gate when you are talking about short channel devices. So, GSD is not only given by the long channel equations, when you are talking about the short channel equation, then you need to include these correction factors, which will give you the less error in your calculations. So, if we plot these parameters with respect to VDS, considering this is what non saturation region and this is what the saturation region. So, we plotted this graph including the behaviors of channel length modulation, drain induced barrier lowering to reduce the error. Then we find that in the non saturation region GSD is higher, right, and when VDS is equals to 0, GSD can be given by mu into Cox into W divided by L into VGS minus VT. But beyond this point, when the device entered into saturation, my GSD goes to 0. This transition from non-saturation to saturation is smooth, whereas when you propose some model, it will be it will show a sharp boundaries, right. But when you use all region model or a precise modeling, then the transition from non-saturation to saturation should be smooth. This is interesting to note that GM at VDS is equals to VDS dash, it means this point is approximately equal to GSD measured at VDS is equals to 0 for alpha is equals to 1. So, if we consider alpha is equals to 1, then these two values are approximately same, correct, from this graph. Now, let us see the output conductance. The output conductance means what? As we have said that in the MOSFET, the current is not only due to drain to source, whereas the current, the total current is the sum of IDS plus IG plus IB, because in short channel devices or in practical devices there will be a gate current and there will be a body current. So, if I want to find out the overall conductance, that is G out is equals to delta ID divided by delta VDS, then I can define as delta IDS divided by delta VDS plus delta IG divided by delta VDS plus delta IB divided by delta VDS. Following superposition theorem, I can simply say this is nothing but GSD plus GGS plus GBS or GBD, and this is GGD, right. So, overall transconductances can be given by GSD plus GGD plus GBD, right. Now, this can be seen from the characteristic which we plotted as ID versus VD. This is output characteristic. We know that output characteristic in non-saturation region is linearly rises, then it gets saturated. Because of CLM there is a slope, finite slope, and if VDS is very high, then there will be an impact ionization occurs and the current rises, right. Now, if we plot GM in log scale, it shows this kind of trend, which simply shows that because of impact ionization, then GM increases. Now, we can analyze these two graphs for short channel and long channel devices. As you can see, this is plotted for short channel device and this is plotted for long channel device. So, in the presence of CLM and Dibble, right, GSD is large in short channel device, and hence you can see from here, whereas in the long channel device what happens, there is an impact ionization. You can see there is an impact ionization picture governed in, right. So, this two plots, which is nothing but the same plot plotted for different values of VGS, right, for two different conditions where channel length is very small and the channel length is large. In addition to all these parameters, let us see what is the impact of extrinsic resistances. In our previous lectures also, we have seen that this is the MOSFET what we are talking about. We said that this is our source terminal, this is gate terminal, drain terminal and the body terminal. But when you connect the MOSFET, there are some extrinsic resistances, right. These extrinsic resistances are coming due to doping, due to external wires, etc. So, because of that, the effective gate to source voltage, effective body to source voltage or effective drain to source voltage is changed, right. We defined these parameters as VD cap, VGS cap in our previous lecture, and we have also seen that the current now is no longer given by the simple equation, rather there is a factor of 1 plus beta r into VGS is coming into picture, right. So, now the current is no longer given by simply W by L into mu into COX dash into VGS minus VT into VDS minus alpha into VDS divided by 2. There are some factor which is dependent on VGS minus VT. Now, when you are going to calculate the transconductance or the output conductance, then this factor will also come into picture. That is what the correction factor. It means when you are going to take the derivative of this current, then you should take care of these parameters or the second order effects what we have discussed in our previous lectures. So, if you calculate Gm, then there will be Gm effective, which is nothing but delta Ids divided by delta Vgs. Now, you have to include this parameter, this is also a Vgs parameter, right, or Vgs dependent function. So, this will give you Gm divided by 1 plus Gm into RSE, where RSE is what? The E stands for external, RDE external resistances, right. In addition, if you see the body resistance, for example, this is N plus, this is N plus, and there is body. So, this is source, this is drain, and there is body. There is a body resistance which is RBE. Now, what will happen because of the impact ionization or because of the high field, there will be a current flowing into it. This current is what? IDB. This IDB current will create a voltage drop here. Because of this voltage drop, VSB is what? Influenced, right. The source to body voltage will get influenced. So, let us consider if the current flowing into this direction, which causes a voltage drop in the external body resistance, then VSB is what? Decreases. If VSB is decreases, threshold voltage decreases, current increases. So, there will be a positive loop occur, right. Because of that, what will happen? The overall output effective conductance will also increase by 1 plus GMB into RBE, right. So, we are not going to do a detailed calculation, but you can simply consider this factor and include in our basic equations what we have derived for overall output conductance, right. So, let me summarize this lecture. In this lecture, we have discussed about the gate transconductance, the source to drain conductance, the body transconductance in strong inversion. We said that gate transconductance depends upon device operation and it is strongly influenced by velocity saturation. We have discussed that how the two different transconductance or conductance are interrelated, as GMB by GM can be defined as dVt divided by dVSB, or it can be defined as gamma divided by 2 into square root of phi naught plus VSB n minus 1 and so, right. We have said that we have also discussed that the impact of CLM and Dibble, it needs to be considered to accurately model the GSD. To reduce the error, we need to include the second order effect in calculation of the derivative of the current. At last, we have seen that the extrinsic resistances modify the small signal parameter extensively, and we need to take utmost care while calculating these parameters, considering the extrinsic resistances, the second order effects like channel length modulation, drain induced barrier lowering, velocity saturation, etc. So, we will stop here for today. Until then, take care.